Download this code from codegive.com, link in the description below. OK, let's dive deep into estimating the memory consumption of large language models, LLMs, during inference and fine-tuning. This is a crucial aspect of deploying and training these models effectively, as it directly impacts hardware requirements and cost. Why is memory estimation important? Hardware planning. Memory consumption dictates the type and amount of GPUs, or CPUs if you're daring, needed to run your model. You don't want to get halfway through a fine-tuning run and run out of memory. Batch size optimization. Memory is a limiting factor for batch size. Larger batches generally lead to better GPU utilization but require more memory. Model optimization. Understanding memory usage can guide you toward memory-efficient optimization techniques like quantization, pruning, and knowledge distillation. Deployment costs. Cloud providers charge based on the resources you use, and memory is a significant factor. Feasibility assessment. It helps determine if you can fine-tune a model on your available hardware or if you need to explore alternative strategies like parameter-efficient fine-tuning, PEFT. Components contributing to memory consumption. When an LLM is loaded into memory, RAM or GPU memory, the following aspects affect the amount of memory that would be used. 1. Model parameters. This is the largest contributor. LLMs have billions or even trillions of parameters, weights. The data type used to store these parameters, example FP32, FP16, int8, drastically impacts memory usage. 2. Activations. Activations are the intermediate outputs calculated during the forward pass. They are used during backpropagation in training. The size of activations depends on the model architecture, batch size, sequence length, and hidden layer dimensions. 3. Gradients. During training, fine-tuning, you need to store gradients for each parameter. This essentially doubles the memory footprint of the parameters themselves. 4. Optimizer states. Optimizers, like Atom, often maintain extra state for each parameter, example momentum, variance. This can significantly increase memory usage, often by a factor of 2 or more compared to the raw parameter size. 5. Input data. The input sequences, text, images, etc., need to be loaded and processed. The size depends on the sequence length, batch size, and the data type used for representation. 6. Buffers and temporary variables. The deep learning framework, PyTorch, TensorFlow, uses temporary buffers for various calculations. These contribute to the overall memory footprint, although they are usually smaller than the other components. How to estimate memory consumption. 1. Model parameter size calculation. Determine the number of parameters. This is usually reported in the model's documentation or architecture definition. Identify the data type. FP32, single precision floating point, 4 bytes, FP16, half precision, 2 bytes, BF16, brain float 16, 2 bytes, int8, 8-bit integer, 1 byte. Calculate the size in bytes. Size, bytes, equals number of parameters. Bytes per parameter. Convert to MB/GB. Divide by 1024 sub 2 sub 4 MB, 1024 sub 3 sub 4 GB. Example, Python code. 2. Estimating activation memory. Model architecture. The specific model architecture will heavily influence activation sizes. Pay close attention to the number of layers, hidden dimensions, attention heads, and other architectural details. Asterisk sequence length asterisk longer sequences lead to larger activation tensors. Asterisk batch size asterisk the batch size directly scales the activation memory. Asterisk data type asterisk the data type, FP32, FP16, affects the size of each activation element. Formula asterisk. Explanation. Asterisk number underscore layers, how many layers are in our LLM? Asterisk batch underscore size, number of independent samples processed together in one forward/backward pass. Asterisk sequence underscore length, number of tokens in one input sequence. Asterisk hidden underscore dimension, this specifies the size of hidden states within the neural network. Asterisk bytes underscore per underscore element, this depends on the data type used for storing activation values. Example, conceptual. Let's say we have a simplified transformer with asterisk number underscore layers equals 12. Asterisk batch underscore size equals 32. Asterisk sequence underscore length equals 512. Asterisk hidden underscore dimension equals 768. Asterisk bytes underscore per underscore element equals 4, FP32. Important notes on activations asterisk. Asterisk the above is a simplified estimate. Some layers might have intermediate activations with different dimensions. Asterisk transformer models have attention layers that generate attention weights, which also contribute to activation memory. Asterisk activation memory is dynamic and changes during the forward pass. Asterisk gradient checkpointing, explained below, can significantly reduce activation memory. 3. Estimating gradient memory, fine-tuning. Asterisk during fine-tuning, you need to store gradients for every parameter in the model. Asterisk the size of the gradients is the same as the size of the model parameters, so you essentially double the memory required for parameters. Asterisk if you're using mixed precision training, example FP16 parameters but FP32 gradients, the gradient memory will be larger than the parameter memory. Formula asterisk. 4. Estimating optimizer state memory, fine-tuning. Asterisk optimizers like Atom maintain extra state, example momentum, variance, for each parameter. This can increase memory consumption significantly. Asterisk Atom typically requires at least 8 bytes per parameter, for FP32 momentum and variance. Some variations require even more. Example asterisk. Total memory estimate, fine-tuning. Memory optimization techniques. 1 Mixed precision training asterisk using FP16 or BF16 for model parameters and activations can significantly reduce memory usage compared to FP32. Modern GPUs have hardware acceleration for FP16/BF16, making it a very effective optimization. 2 Gradient checkpointing, activation checkpointing. Instead of storing all activations during the forward pass, gradient checkpointing only stores a subset and recomputes the others during backpropagation. This trades computation for memory. 3 Quantization asterisk reducing the precision of model weights and activations, example to int8, can significantly reduce memory usage. There are various quantization techniques, example post-training quantization, quantization-aware training. 4 Parameter efficient fine-tuning, PEFT methods like LoRa, adapter layers, and prefix tuning only train a small subset of the model parameters, drastically reducing memory requirements. This allows you to fine-tune very large models on limited hardware. 5 Zero redundancy optimizer. Zero is a memory optimization technique that partitions the model parameters, gradients, and optimizer states across multiple GPUs. This allows you to train models that wouldn't fit on a single GPU. It's typically used with deep learning frameworks like PyTorch, using libraries like DeepSpeed or FairScale. 6. Offloading * move some of the model parameters or optimizer states to CPU memory, RAM, or even disk. This can free up GPU memory, but it will slow down training significantly due to the slower memory access. 7. Batch size reduction * A smaller batch size directly reduces activation memory. However, this can also reduce GPU utilization. 8. Sequence length reduction * shortening the input sequence length reduces activation memory. This might not be feasible if your task requires long sequences. 9. Knowledge distillation train a smaller and efficient model by transferring knowledge from a bigger model. Code example, gradient checkpointing in PyTorch. Tools for monitoring memory usage. *torch.cuda.memory_summary, PyTorch provides a detailed breakdown of GPU memory usage in PyTorch. *NVIDIA SME * a command line tool to monitor GPU usage, including memory, on NVIDIA GPUs. Run it in a terminal. *TensorBoard * can be used to track memory usage during training. Profiling tools * PyTorch Profiler, TensorFlow Profiler, etc., can provide detailed insights into memory allocation and deal location. Practical tips. Start small * begin with a small batch size and sequence length, and gradually increase them until you encounter memory issues. Experiment * try different optimization techniques and monitor their impact on memory usage. Use memory profiling tools * these tools are essential for identifying memory bottlenecks and understanding how your model is using memory. Check framework documentation * the documentation for your deep learning framework, PyTorch, TensorFlow, will provide information about memory management and optimization techniques. Complete example, estimating memory for fine-tuning a small transformer. Important considerations. Framework overhead * the deep learning framework, PyTorch, TensorFlow, adds its own memory overhead, which can be difficult to estimate precisely. Garbage collection * Python's garbage collection can affect memory usage patterns. Memory fragmentation * memory can become fragmented over time, which can lead to out-of-memory errors even if the total allocated memory is less than the available memory. In conclusion, estimating memory consumption for LLMs is challenging but essential for efficient deployment and training. The techniques outlined above provide a solid foundation for making informed decisions about hardware requirements and optimization strategies. Remember to use memory profiling tools to validate your estimates and identify bottlenecks in your code. Always be prepared to adjust your strategy based on your specific model, data, and hardware. Good luck.